Okay, now we are moving towards integration. And remember what I said at the beginning of the semester. Limits, as x approaches a number of f of x, equals the intended height, right? And if you've got a function, when you take the derivative of the function, that's instantaneous velocity. The derivative is instantaneous velocity at a specific x value or c value. And then finally, when you differentiate, you're going to use uppercase f of x. You're going to approximate area. One of the uses is find the area under a curve. The curve could actually be represented by a straight line. For each problem, approximate the area under the curve over the given interval. This is the two x values using 4 left endpoints. And I'll show you what that means. You may use the graph provided to sketch the curve and the rectangles. Okay, first thing we're going to do, and I've already done this, is I've drawn that. And then between the intervals of 3 and 7, so let me do this. All of this is the area we want to do, but we need to use rectangles, because before they had calculus, they had to come up with ways to find area under weird shapes. This isn't too weird. That's a trapezoid. You could just do a trapezoid, but in a few minutes there will be curves. So, and notice those rectangles actually go above that line, but we're just approximating. So we're going from 3, so our x values are 3, 4, 5, 6, and 7. However, we're using the 4 left endpoints. So if we're going from left to right, 1, 2, 3, 4. So think about it this way. We're looking at these corners right there. And actually, I didn't draw this very well. Well, yeah, I drew it okay. So you plug y of 3 into the function. So 3 divided by 2 is 3 halves, or 1.5, plus 4 is the height of 4.5. Yeah, I didn't draw that well, or I just went up a little bit too far. There we go. And then we're going to plug, so we got 4.5, and I put it right there. Then we plug 4 into there. Well, 4 divided 2 is 2. 2 plus 3 is 5. So there we are at a height of 5. And then we plug 5 in there. 5 divided by 2 is 2.5. 2.5 plus 3 is 5. And clearly we're going up by 0.5 each time. Then you can just fill in the graph. Oh yeah, we don't need this one. Well, look at what we have now. We have heights. And we have widths. So each one of those widths, so if you're looking at this rectangle, each one of those widths is 1, and this height is 4.5, then 5, then 5.5, then 6. Well, so the area under the curve, and I'm going to show you introduce integration notation. So the area is equal, so it looks like this kind of weird S, that's a summation kind of, and we're going from 3 to 7, and I'm just going to call this f of x for right now. And what it equals is, so the first rectangle is 1 times 4.5. The second rectangle is 1 times 5. then 1 times 5.5, and then, whoops, plus 1 times 6. So let's see. 4.5 and 5.5 is 10. 6 and 5 is 11. So the area under that curve from 3 to 7, and you could actually write that, the function name in right there. We could do that. We're going to tack on that dx. Is approximately 21 units squared. So we don't have an exact area underneath that curve, but using the leftmost points, so we draw our rectangles up until it hits the line, and then we draw a rectangle. And we get those heights. You can also get those heights by plugging the x values in to find the y values. All right, let's do all right. Oh, I know why I was doing that one, because now the previous one is using the rightmost angles. Here, let me pause this. Okay, so now we're using the right endpoints. So we're going from -4 to 0. But now when we draw our and then all I did was that red line is I sketched this. I started here at 5, and I went down 1 over 2, down 1 over 2, and then I went up 1, back 2, till I had that line drawn. And now when we draw our rectangles, we draw the right point side. So let me start here. We hit right there, and then we draw a rectangle. And then we hit the line up there, and we hit the line. Okay, if you do your table of values, that's just a really good way to organize the information. Each of those widths are 1. And now it's -4, -3, -2, -1, and 0. But now we're going from right to left, and we're only using, not that. We're only using those 4. So when we plug 0 into this, 0 plus 5, we're at a height of 5. And then when we plug in -1, well, the opposite of negative is positive, so 1/2 plus 5 is 5.5. And look at, we're going to be going up. We have a pattern now, so we can put 6 and 6.5. And then if you just multiply the length, well, in this case the height, times the width or the base, and then add all of those together. So 6.5 times 1 is 6.5. And again, 5.5 plus 6.5 is 12. And 6 plus 11 is 11. I mean, 6 plus 5 is 11. So we have the area approximates as we go from -4 up to 0, negative x over 2 plus 5, tack on that dx. This dx right here always accompanies this notation. If you don't have the dx, dy, dt, d whatever, then you're not integrating. You're not finding the area under a curve or volume or whatever. So now you can put the approximation, and we got about 23. And remember, this is area, so units squared. All right, that is it. And then I'll do a midpoint and a trapezoid one.